Hello, and welcome to Mysteries of Reality, where we journey beyond the known and explore the deepest mysteries of the universe. I'm Jonathan Eldridge, your guide through the cosmos, and I'm thrilled that you're here. Welcome to Quantum Mechanics for the Curious Mind. Today, we embark on an adventure into the strange and fascinating world that governs the behavior of the smallest particles in the universe. Quantum mechanics isn't just a branch of physics. It's a revolutionary framework that challenges our everyday intuition and opens up a realm where matter and energy behave in ways that defy classical expectations. In this video, we'll unravel the core ideas of quantum mechanics, explore its history and key experiments, and discuss how these concepts not only explain the nature of reality, but also drive modern technologies. Whether you're a seasoned science enthusiast or a curious newcomer, prepare to have your mind expanded as we journey into the heart of the quantum world. Historical foundations, from classical to quantum. Our journey into the quantum realm begins with a look back at the evolution of physics, from the well-trodden paths of classical mechanics to evolutionary ideas to give birth to quantum mechanics. For centuries, classical physics reigned supreme, describing the world with the precise laws of Newton, Maxwell, and others. In this framework, objects moved predictably, forces could be calculated with great accuracy, and the universe was seen as a clockwork mechanism where cause and effect were clearly defined. From the predictable orbits of planets to the elegant equations governing electromagnetism, classical physics provided a robust understanding of everyday phenomena. However, as experimental techniques improved at the dawn of the 20th century, cracks began to appear in the classical picture. Phenomena such as the blackbody radiation problem, the photoelectric effect, and atomic spectral lines could not be reconciled with classical theories. Max Planck's work on blackbody radiation introduced the radical idea that energy is emitted in discrete packets, or quanta, rather than in a continuous flow. This concept marked the first departure from classical thought, suggesting that the microscopic world operates according to principles that defy everyday intuition. Building on this revolutionary idea, Albert Einstein explained the photoelectric effect by proposing that light itself is composed of quanta, particles of energy now known as photons. His insight not only confirmed Planck's hypothesis, but also challenged the classical wave theory of light, setting the stage for a new understanding of electromagnetic phenomena. At the same time, Niels Bohr's model of the atom introduced quantized energy levels for electrons, providing a framework to explain why atoms emit or absorb light at specific wavelengths. Bohr's theory, though initially a hybrid between classical and quantum ideas, paved the way for a more comprehensive quantum theory. These groundbreaking ideas culminated in the development of quantum mechanics, of a theory that fundamentally redefined our understanding of nature. It introduced the notion of wave-particle duality, where particles such as electrons exhibit both particle-like and wave-like characteristics, and the uncertainty principle, which limits the precision with which certain pairs of properties, like position and momentum, can be known simultaneously. Quantum mechanics revealed that, at the microscopic scale, nature is inherently probabilistic rather than deterministic, a stark contrast to the certainty promised by classical laws. Thus, the historical transition from classical to quantum physics is not merely a chronological progression. It represents a profound shift in our understanding of reality. Classical physics laid the groundwork by describing the macroscopic world with remarkable accuracy, but its limitations in explaining the behavior of light and matter at atomic and subatomic scales necessitated a radical rethinking. Quantum mechanics emerged as a response to these challenges, opening up a realm where uncertainty, probability, and duality are fundamental features. This evolution of ideas continues to inspire new generations of scientists as they seek to unravel the mysteries of the universe, bridging the gap between the familiar and the unfathomable, the basic principles, waves, particles, and uncertainty. At the heart of quantum mechanics lie several fundamental principles that append our classical understanding of the world, revealing a reality that is as intriguing as it is counterintuitive. One of these core concepts is the dual nature of matter and energy, where entities such as electrons and photons behave both like particles and waves. This phenomenon, known as wave-particle duality, was first hinted at by experiments that demonstrated interference and diffraction patterns, behaviors traditionally associated with waves. For instance, when electrons pass through a double-slit apparatus, they create an interference pattern on a detector screen, suggesting that they exhibit wave-like properties. Yet, when measurements are made to detect which slit an electron passes through, the interference pattern disappears, and the electrons behave like discrete, localized particles. This duality challenges our everyday perceptions and forces us to accept that the microscopic world does not conform to the classical distinction between waves and particles. Complementing wave-particle duality is the Heisenberg uncertainty principle, of a concept that imposes a fundamental limit on how precisely we can measure certain pairs of physical properties simultaneously. For example, the more accurately we determine a particle's position, the less precisely we can know its momentum, and vice versa. This isn't a limitation of our measurement instruments, but rather an intrinsic feature of nature at quantum scales. The uncertainty principle tells us that at the quantum level, particles do not have well-defined properties until they are observed, and even then, the act of measurement influences the system. This inherent fuzziness is not merely a reflection of experimental imprecision. It is a cornerstone of quantum theory that reshapes our understanding of reality itself. Together, these principles, wave-particle duality and the uncertainty principle, reveal a universe where certainty is replaced by probabilities, and where the very nature of matter and energy is fundamentally linked to observation. They invite us to move beyond the deterministic world of classical physics into a realm where particles can exist in multiple states simultaneously, and where outcomes outcomes can only be described in terms of likelihoods. As we continue to explore and harness these quantum principles, we not only unlock the mysteries of the microscopic world, but also pave the way for revolutionary technologies, such as quantum computing and cryptography, which promise to transform our future. Quantum experiments, the path to understanding the exploration of quantum mechanics, is deeply rooted in a series of groundbreaking experiments that have illuminated the bizarre and counterintuitive behavior of particles on the smallest scales. These experiments have not only challenged our classical worldview, but also paved the way for a profound new understanding of the nature of reality. One of the earliest and most influential experiments is the double-slit experiment, originally performed with light and later with electrons. This experiment revealed that particles can display both wave-like and particle-like properties, a phenomenon known as wave-particle duality. When particles pass through two closely spaced slits, they produce an interference pattern on a detector screen, a signature of waves interacting. However, when scientists attempt to measure which slit a particle goes through, the interference pattern disappears and the particle behaves as a discrete entity. This result forced physicists to accept that the act of observation fundamentally alters the state of a quantum system, a radical departure from classical expectations. Another key experiment is the Stern-Gerlach experiment, which demonstrated the quantization of angular momentum. In this experiment, a beam of silver atoms was passed through a non-uniform magnetic field, causing the atoms to split into discrete paths, corresponding to quantized spin states. This splitting provided clear evidence that certain physical properties, such as spin, can only take on specific, discrete values rather than a continuous range. Such quantization is a cornerstone of quantum theory and highlights the intrinsic granularity underlying the behavior of particles. Subsequent experiments further solidified the foundations of quantum mechanics. Experiments involving quantum entanglement, such as those testing Bell's inequalities, showed that particles can become interconnected in ways that defy classical locality. In these experiments, measurements on one particle instantaneously affect the state of its entangled partner, regardless of the distance between them. These results, repeatedly confirmed through rigorous testing, underscore the non-local nature of quantum mechanics and have profound implications for our understanding of causality and information transfer. Advancements in experimental techniques have also given rise to practical applications, driving technological innovation. The development of quantum optics experiments, which manipulate and measure individual photons, has led to the emergence of quantum cryptography and quantum computing. These technologies leverage the principles of superposition and entanglement to perform tasks that are impossible for classical systems, opening new frontiers in secure communication and computational power. Together, these quantum experiments form the bedrock of our modern understanding of the subatomic world. They reveal a universe that is inherently probabilistic, where the act of measurement plays a crucial role classical notions of continuity and locality no longer apply. Each experiment has chipped away at the veneer of classical intuition, revealing a realm where particles are not merely points moving in space, but dynamic entities existing in a superposition of states until observed. In essence, the path to understanding quantum mechanics is paved with experiments that continuously challenge our perceptions and expand our knowledge. From the elegant interference patterns of the double-slit experiment to the profound implications of entanglement, these experiments invite us to rethink the very nature of reality. They serve as both a testament to human ingenuity and a reminder that the universe operates on principles far stranger and more beautiful than our everyday experiences suggest. Interpretations of quantum mechanics, seeking meaning in the uncertainty. Quantum mechanics, with all its mathematical precision and experimental success, leaves us with a deep philosophical puzzle. What does it all mean? Over the decades, scientists and philosophers have proposed various interpretations to make sense of the inherent uncertainty and peculiar phenomena observed at the quantum level. While the mathematical formalism of quantum mechanics accurately predicts experimental outcomes, it does not by itself explain the nature of reality. This gap has given rise to several interpretations, each attempting to reconcile the abstract theory with our intuitive notions of the physical world. One of the most widely taught interpretations is the Copenhagen interpretation. In this view, quantum systems exist in a superposition of states until they are observed. The act of measurement causes the wave function, a mathematical description of probabilities, to collapse into one definite outcome. This interpretation emphasizes the role of the observer and posits that the inherent randomness is a fundamental aspect of nature. Although it has been extremely successful in guiding experiments and technology, the Copenhagen interpretation leaves many with a sense of discomfort over the seemingly magical role of observation in determining reality. In contrast, the many worlds interpretation takes a bold stance. Every possible outcome of a quantum event actually occurs, each in its own branching, parallel universe. Rather than a single outcome emerging through collapse, the universe is constantly splitting into countless, coexisting realities where every possibility is realized. This interpretation eliminates the need for wave function collapse and restores a form of determinism at the cost of an ever-expanding multiverse, a concept that stretches our imagination and challenges our understanding of existence on a cosmic scale. Other perspectives, such as pilot, wave theories, or de Broglie, Bohm theory, offer a more classical-like picture. In these theories, particles have well-defined positions at all times, guided by an underlying pilot wave that determines their trajectories. This approach retains determinism and provides a clear picture of how particles move, but it introduces non-locality, the idea that changes in one part of the system can have instantaneous effects elsewhere, which remains a point of debate among physicists. Yet another approach is the relational interpretation, which suggests that the properties of quantum systems are not absolute, but depend on the relationship between the observer and the observed. In this view, different observers might describe the same event in different, equally valid ways, emphasizing the contextual nature of quantum properties. This interpretation reframes the discussion of uncertainty by suggesting that there is no single, objective reality, but rather a network of interrelated observations. These interpretations, while diverse, share a common goal: to provide a conceptual framework that bridges the gap between the counterintuitive mathematics of quantum theory and our desire for a coherent picture of reality. They invite us to question what it means for something to exist and challenge us to redefine notions like determinism, locality, and even reality itself. Ultimately, the quest to interpret quantum mechanics is as much a philosophical journey as it is a scientific one. Each interpretation offers unique insights and raises further questions about the nature of observation, information, and existence. As research advances and our experimental techniques become more refined, these interpretations may evolve or even merge, guiding us closer to a unified understanding of the quantum world. For now, the uncertainty inherent in quantum mechanics continues to inspire debate, wonder, and a profound appreciation for the mysterious depths of the universe. Applications and technological impact, quantum in the real world. The abstract principles of quantum mechanics have not remained confined to theoretical musings. They have paved the way for a host of transformative technologies that permeate our everyday lives. At the heart of modern electronics lie quantum phenomena, the very operation of semiconductors, essential components in devices like smartphones, computers, and solar cells, relies on the quantum behavior of electrons in solid materials. Transistors, which form the building blocks of microchips, operate through the manipulation of electron flow at the quantum level, enabling rapid and efficient computation that has fueled the digital revolution. Another quintessential application of quantum mechanics is the laser. The concept of stimulated emission, predicted by quantum theory, underpins the operation of lasers, which emit highly coherent and focused beams of light. Lasers have found widespread use across various fields, from medicine, where they perform precise surgeries and eye treatments, to telecommunications, where they facilitate high-speed data transmission over optical fibers. Their precision and versatility continue to drive innovation in both industrial and consumer applications. Quantum mechanics also forms the foundation of emerging technologies that promise to revolutionize our future. Quantum computing, for instance, harnesses the power of quantum superposition and entanglement to process information in ways that far exceed the capabilities of classical computers. Unlike traditional bits that represent either 0 or 1, quantum bits, or qubits, can exist in multiple states simultaneously. This enables quantum computers to perform complex calculations at speeds that could solve problems ranging from cryptography and optimization to simulating complex chemical reactions and materials. In the realm of secure communications, quantum cryptography leverages the principles of quantum quantum mechanics to create unbreakable encryption. Quantum key distribution, QKD, allows two parties to share a secret key with security guaranteed by the laws of physics. Any attempt at eavesdropping inevitably disturbs the quantum states involved, alerting the communicating parties to potential security breaches. This level of security is poised to protect sensitive information in an increasingly digital and interconnected world. Beyond these applications, quantum sensors are emerging as powerful tools for precision measurement. These devices exploit quantum effects to achieve levels of sensitivity and accuracy far beyond classical instruments. From gravitational wave detectors to atomic clocks that define international time standards, quantum sensors are expanding our ability to measure fundamental physical phenomena with unprecedented precision. The impact of quantum mechanics is not limited to technological advancements. It has also spurred significant progress in our scientific understanding. Quantum experiments and technologies continue to push the boundaries of research, leading to new insights into the nature of matter, energy, and even the fabric of space-time itself. As quantum technologies evolve, they are expected to unlock further innovations that could transform sectors such as medicine, finance, and environmental science. In summary, the applications and technological impact of quantum mechanics exemplify how fundamental scientific principles can lead to groundbreaking real-world innovations. From the microchips in our devices to the lasers that power our communications, and from the promise of quantum computers to the security of quantum cryptography, the influence of quantum theory touches nearly every aspect of modern life. This journey from abstract theory to practical application not only highlights the remarkable versatility of quantum mechanics, but also continues to inspire a future where our understanding of the quantum world reshapes technology and society in profound ways. The future of quantum mechanics, open questions, and new frontiers. As we look to the horizon of scientific inquiry, the future of quantum mechanics promises to be as revolutionary as its past. Despite its impressive success in explaining the microscopic world, quantum mechanics still leaves us with profound questions and challenges that invite further exploration. One of the most compelling open questions is how to reconcile quantum mechanics with general relativity. While quantum theory governs the realm of the very small, general relativity describes the gravitational behavior of massive objects and the fabric of space-time. The quest for a theory of quantum gravity, whether through approaches like string theory, loop quantum gravity, or entirely new frameworks, remains one of the greatest challenges in modern physics. In addition to unifying the fundamental forces, researchers are pushing the boundaries of quantum mechanics through emerging technologies. Quantum computing, for example, aims to harness the unique properties of superposition and entanglement to solve complex problems far beyond the reach of classical computers. As quantum processors scale up and error correction techniques improve, and we may soon witness a paradigm shift in computation that could transform fields ranging from cryptography to drug discovery. Another frontier lies in the realm of quantum materials and sensors. Advances in material science are uncovering new phases of matter, such as topological insulators and superconductors, which exploit quantum effects for novel electronic properties. Similarly, quantum sensors, ranging from ultra-precise atomic clocks to gravitational wave detectors, are set to dramatically improve our ability to measure time, motion, and even the subtle ripples in space-time. Yet, with these advances come deeper philosophical and conceptual questions. What is the true nature of quantum measurement? How does information behave in a quantum system? And can it be preserved across seemingly insurmountable barriers, such as black hole event horizons? These inquiries not only push the boundaries of physics, but also challenge our understanding of reality itself. In essence, the future of quantum mechanics is an open frontier, ripe with both technological promise and fundamental mysteries. As we develop new experimental techniques, forge innovative theoretical models, and integrate quantum ideas into practical applications, we stand at the cusp of discoveries that may redefine our grasp of the universe. The journey ahead is as much about deepening our conceptual understanding as it is about pioneering transformative technologies, ensuring that the exploration of the quantum realm will continue to captivate and inspire for generations to come. Thank you for joining me on this journey into the mind-bending realm of quantum mechanics. If you enjoyed exploring these ideas and want to learn more about the fascinating world of physics, please like this video, subscribe to our channel, and turn on notifications for our latest content. Share your thoughts and questions in the comments below. Let's continue this exploration together. Until next time, keep questioning, stay curious, and remember that the universe is far more mysterious than it seems.